Okay, so let's start. Last week we talked about some basic concepts for programming for VFX. We used VEX, which is the Houdini's scripting language, and we just touched on the very basic concepts, and also we reviewed if then else kind of conditions. So this week we are going to create some creative generative art. So the type of stuff that you cannot, well, you can create with lots and lots of nodes, but here you can see with a few lines of programming you can create amazing visuals that are based on concepts. Anything that you do inside Houdini and any programming that you will be doing, they are based on original concepts and mathematical rules. Okay, so we all have heard of golden ratio. So I just want to create patterns today based on this golden ratio. If you don't know what is golden ratio and what is special about golden ratio, so golden ratio is getting repeated everywhere in nature, and there's a reason for that. So let's say you see it like in animals. Oh, sorry. In animals and plants and flowers and also in architecture. So why we see it more and more, especially in like plants. So there are advantages for that. So when the plants kind of grow in this based on golden ratio and golden angle, they kind of can utilize the positioning of their leaves in a way that all the leaves receive proper sunlight. So the optimal light absorption and also optimal, so the leaves are positioned in an optimal angle, which is 137.5 degree, which I will explain what that number comes from. So it's kind of like help them to avoid obscuring the sunlight. So in terms of mathematics of it, golden ratio is quite, it's a simple math. Actually, if I can tell it in a even more simpler way. So let's say you got like a box here which is 1, okay? So you say 1, and then you say, okay, so let's repeat that, and you get 1, okay? Now, the next box will be the sum of these two. So it's going to be 2. The next box will be sum of all of these. So it's going to be 4. The next box will be sum of all of that. So it's going to be 8. So you see that it just travels through like that, and it grows in a spiral way if I continue. So this kind of this series of numbers in math, if you want to do it, it's going to be 1 plus square root of 5 divided by 2, like 1 plus square root of 5 divided by 2, which is roughly around 1.618. So this is golden number. But when this number, so it's equal to the 2 multiply sine of 54. So where these numbers come from, I will explain it to you. And if you convert it into if you wanted to see it in a so this, let's call this number phi. If you want to say, so I have a circle, how much of this circle, how far, like how can I divide this circle based on the golden ratio? You just do the full circle divided by 1 plus 1.618, and you get somehow approximately 137.5 degree. Okay, so so that might sound like a bit boring, but like, let's have a look at this video to see how interesting is this. So if you I'm a big fan of number fill. If you are interested in math, the fun part of math, this is an amazing channel to follow. So here you see the mathematician Ben Spark talking about why golden ratio is so important in nature and why it is so irrational, looks to us. So I paused the recording video, but I play this. So if in future you want to kind of get an idea of, so any time that you just want to enjoy math and golden ratio, watch this video, okay?
I want to tell you about a very famous number that you've heard about before, but I want to tell you why it is what it is, and it's the golden ratio. A lot of people think the golden ratio is this mystical thing. It is, but not for the reasons they think. But I want to do that, I want to tell you why it's interesting, but I want to do that through a mechanism of flowers. And you may have heard a connection with the golden ratio and flowers before, but I want to show you why that connection is there. For the sake of this little video, I'll be the scribe, but I'd like you to imagine, Brady, that you are a flower. Your job as a flower is to deal with your seeds. It's kind of the job of everything living. You're going to grow some seeds, and we're going to model this flower in a mathematical way. This is not how flowers actually grow, but there are connections. This is the center. When you grow a seed, I'm going to represent that by putting a little blob. That's a seed that you've grown from the center of your flower. And one option you could have is you've got to decide where to put your seeds. And I'm going to give you the option of only how much do you turn around before you grow your next seed. So you put a seed down, and you could turn a bit and put another seed down, kind of growing it. If you don't turn at all, you're going to grow seeds out like this. The first seed goes there. If you don't turn, the next seed goes next to it, and the next one goes next to it. And you're going to grow the seeds out there, and you're going to push seeds out. Actually, I'm adding them on the end, but it would grow from there and push these seeds out in a line. This is a really bad arrangement for a flower. I hope you agree, and I hope you weren't imagining this when you were thinking of a flower.
Because it's a waste of space.
Yeah, there's a whole bunch of circle unused. So the obvious thing, if I'm going to do this model of like, if a flower could just grow by putting a seed and then turning a bit, what would happen if you turn an amount of a turn? So I'm going to talk about fractions of turns. This is a fraction of a turn of 0. If you do a new one here and you turn half a turn each time, then if the first seed goes here, then I think if you turn half a turn, the next one's going to go there. And if you turn half a turn again, keep going in the same direction, it's going to go there and there. And this is also not exciting, but you can kind of see why the decision of turning a half has made 2 lines. And maybe I'm going to call these spokes, because just to get you in the mood, let's do a third. You could probably predict it pretty easily. Seed, turn a third of a turn, or roughly there, third of a turn, roughly there. And you're going to see these 3 spokes sticking out pretty easily. Happy enough with this? I mean, none of these are good flower designs, but the consequences of choosing a number is giving you some patterns. So if I jumped, say, to a 1/10 of a turn, would you care to predict what you'd see?
10 spokes.
Yeah. And so I don't think the spoke behavior is very surprising, and it looks like the denominator of this fraction of a turn is controlling everything. Now I think it's much less obvious if I told you what would happen with 3/10. So with 3/10, if you start here, you turn 3/10 of a turn, you'd skip a couple of the branches, and then another 3/10, you'd skip a couple, you go down here, 3/10, you'd skip a couple and go here. And if you keep going around, you'll end up not repeating yourself for a bit until all 10 are done. You also get 10 spokes. So there's this really nice thing in mathematics called a conjecture. We pretty much have one here. It looks like it's the denominator of the fraction that's controlling the number of spokes. So here's a quick computer model of what we've been talking about. And we can check that with other tests. 4 out of 11, you maybe want to predict what happens.
11 spokes?
You're correct, there are 11 spokes. If you type in some other numbers, there are some surprises. If I do 11 out of 23, you do get 23 spokes, but there's some interesting behavior happening in the middle. And that's actually, it looks like there's kind of 2 spokes, but they're kind of twisted, and that's because this number is quite close to 1/2. And it looks like what numbers you're close to also affect what happens. One surprise that you should watch out for, I mean, if I do 7/10, you know about tenths, you get 10 of them. But then occasionally you catch yourself out, you do 4/10 and you think, oh, 10 spokes, but there aren't. Is 2/5. And flowers can cancel fractions. Or they can't actually, and what's happening is that 4/10 is better described by 2/5. So you've seen lots of bad flowers. This is pretty, but it's not what flowers do. What's interesting is if you change this number very, very slowly, and you realize that a tiny change gives you very different behavior. So this number is changing ridiculously slowly, but even a small jump is giving us spirally shapes, and very quickly they stop looking like spokes.
What are you changing? Just the top number?
The number is the fraction of a turn before I grow each seed. So this number that's here is 0.401 of a turn when I grow a new seed, and that's already enough to stop it going in lines, and it's starting to bunch together, and this is already looking a prettier thing for a flower. It's also nicely hypnotic if you need to hypnotize people. You start seeing things kind of turning one way, but also maybe turning the other way, and you see spokes arriving and disappearing, and this is already a better flower.
You're using more of the space.
I'm using it much more efficiently. Now, I'm not saying flowers are thinking about this, but somehow they do this efficiently, and we've got now an obvious question is there a fraction of a turn that is an efficient one? What's really lovely about this is you can see rational numbers arriving. You can see that I'm not at a third, but already the number 3 is dominating everything. It's like hunting for big game. You can hear these animals coming in the undergrowth. You can see it. This third is about to arrive. We're at 0.329 now, and as soon as we hit exactly a third, we're going to get those 3 spokes. And it's really nice to see it arrive and then disappear. So it's about to get there. As soon as we hit 0.3333 exactly, as long as it carries on forever, you will see our 3 spokes. And then it's gone, and we're into other numbers. If you put a number in for a fraction of a turn, and it is a fraction, i.e. it has a denominator, it's going to give you spokes. And so maybe we're into familiar territory from many other discussions about numbers. Maybe you could suggest a number, Brady, that you could type in that wouldn't give me spokes.
Which is an irrational number. The square root of 2.
The square root of 2? What do you think you're going to see?
Kind of spiralness. Ooh.
It looks less like it's got spokes, but you can kind of count them. And it turns out that this is definitely an irrational number. I'm approximating an irrational number on a computer, but this arrangement looks much better. So it sounds like you've hit upon the idea of maybe flowers need to turn an irrational amount of a turn. But there are other irrational numbers. I'm going to type in 1 over pi, because pi is a lot of people's favourite irrational number. This surprised me. Think about what you might see. We know it can't produce spokes because pi is irrational. Now, they're not quite spokes, but they're slightly curved spokes, and there are, in fact, 22 of them, just to save you counting. I don't know if 22 rings a bell to do with pi, but if the older generation used to get taught that pi was pretty much exactly the ratio 22 over 7. It's not quite, but it's unreasonably good. And you can see on this diagram that it's unreasonably good because this is irrational, but it's really well approximated by something to do with the number 22. In fact, what I love about this diagram is you can see another approximation for pi buried in the middle. There aren't 22 spokes in the middle, there are 3. 3 is a very well-known approximation for pi. In fact, if I carried this diagram on really big, you'd see lots of rational approximations for pi in the arrangements of seeds in a flower, or a mathematical flower. But what it also tells you is that pi is not very irrational. It looks like root 2 was more irrational. So actually the obvious question, which is turned up in lots of situations and maybe in other videos from me, is there one that's the most irrational? And there is, and I'll show it to you, and then I'll show you why. So here it is. If I jump to the square root of 5 minus 1 over 2, you get this. This is the golden ratio of a turn. And what's lovely about it is you can see spokes, but you can see them going in both directions. They're kind of crossing over both ways, and you can try and count them. And if you do, you get Fibonacci numbers. And if you go and look in the real world, this is the bit that a lot of people claim, is that this is what sunflowers do. So if I hide the seeds there, that's the arrangement of seeds in the head of a sunflower. That's not generated by a computer. This is a flower doing something to be efficient. And if I put the seeds back and hide it, the correlation between those placements is almost frightening. And what's lovely about it is that no other number works. So if I start this animating again, the spokes are obvious. And this kind of unravels, and already you can see these spokes unraveling, and they're obvious spokes. We could count the spokes and figure out what rational number it was near. So the golden ratio looks like it's the best one, but I want to show you on paper why it's the best one. And I'm going to do that by starting with pi, because it's a good place to start. But pi is an irrational number that apparently is not very irrational. And we kind of already know that it's approximated well by a rational number. But let me show you how you can sort of quantify that. So I'm going to say that pi is 3 plus a bit. I don't think that's controversial. But what I'm interested in is writing this number pi, which I can never really write down in full, which is why we have the symbol for it. Can I write it in a way which looks more like a fraction instead of like a decimal? And so 3 plus a bit isn't very helpful, but I could say, since this bit is less than 1, otherwise it would be 4 plus a bit, right? Then I could say this is 3 plus 1 over something. And I could find out what that something is on a calculator. I could take away the 3 and I get the something. And then I could do 1 over that, or x to the minus 1, to find out what it is. And it actually is 7 point something. So I'm going to write this 1 over 7 plus a bit. The words a bit are not sort of mathematically recognized terminology, but you get the idea. So I could carry on. I know that it's 3 plus 1 over 7 plus a bit, and I could write that as 1 over something. And that's on my screen now, so I could take away the 7 and get the bit and do 1 over that. And I get 15 and a bit. I can start writing 15 plus a bit. Instead of doing the bit now, I'm just going to go straight in with 1 over something. Take away 15, get the bit, x to the minus 1, do 1 over it, and I get 1 and a bit. Take away 1, do the bit. It's a very small bit this time, and I get 292. And you can see that if this number is truly irrational, I could just keep going. And actually this thing here is called the continued fraction for pi. And something very obvious happens with the pi is that you get a very small number here and then you get a very large number here. In the trade they call it truncating, but if you chop the continued fraction at a certain point, you'll get an approximation. So 3 and a 7th is 22 over 7. It's a good approximation for pi. If you chop it there, you get an approximation. If you chop it there, if you chop it there. But because this number is massive, and it's 1 over that number, this additional bit is tiny.
Becoming more and more trivial.
Well, actually after that it goes back to being some 1s in the continued fraction. But that particular point means that you don't add very much accuracy at those 2 levels of truncation, which means it was really accurate before, which means the step before that was ridiculously good, which means pi is well approximated quite early on by a rational number, which is why I'm going to claim it's not very irrational and why when you saw the diagram of it, it looks like it had spokes. So looking at the continued fraction, the question is, what would the most irrational number look like? It would be the one with a continued fraction that doesn't have any large numbers in it. So I'm going to claim that this is a pretty good candidate. I'm going to call it x. The continued fraction would be, well, let's just start with 1, but then the continued fraction would go 1 over the smallest whole number, 1. And it would have a 1 here, and it would have a 1 here. We have a 1 here. And this is something that a lot of people do recognize. It's an odd thing to ask what it is, but whatever it is, it will be badly approximated any time you truncate it because these numbers are small. Now, just as a little heads up, I'm just going to tell you that root 2 has a continued fraction as well. 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, and it carries on like that. Which is incidentally why root 2 looked pretty good on our diagram, because although these are not the smallest numbers, they're consistent and they stay small. Where I want to get to with this video, you might know the answer, but I want to prove it, is what is this number? I'm going to solve this. This is an infinite thing, but we can solve this surprisingly easy because it carries on forever. Let me point out something which I think is obvious when someone points it out, which is that this thing is the same as the whole thing. It is x, which means I can sort of grab that thing and call it x, and I can rewrite this equation as x equals 1 plus 1 over x. And that looks much less scary. In fact, it's a quadratic equation, which I'm going to solve. I'm sure people watching this video would have their favorite way of solving quadratics. I'm going to do maybe not quite the quadratic formula. I've seen a friend of mine called Matt Parker try this with a quadratic formula. There's a better way. I'm multiplying by x to get x squared equals x plus 1. I'm going to rearrange it onto one side. I've got x squared minus x minus 1 equals 0. At this point, a lot of people reach for the quadratic formula, that minus b plus or minus the square root. I'm going to complete the square, which is where the formula comes from. So I'm going to realise that if I write x minus a half squared, that would square to give me the x squared. It would also give me the minus x I need.
Okay, I think this is enough so far. So you got the idea of, let me just, you got the idea of like why this number is so efficient in nature. It's because it generates a pattern that can distribute like points very efficiently. So if you want to regenerate that in Houdini, so I'm going to create a pattern that redistributes points efficiently in Houdini. So we need some basic information. So let's say we need number of points. So like how many points you want to generate. So if I go to, we go to the, yeah. So like if we, so we're gonna, so let's say this is the center of your flower or pattern, okay? So like how many points you want to generate around it. So that's number of points. Then you need a position of these points. So you're gonna say that, okay, this is the first point, the second point would be here, the third point would be there. So like the positioning of them. Also, you need like radius, like how far this point is from the center. This point is that much, but this point here is like much further back. So radius, this is radius. and then the angle. So let's say this point, if let's say this, we consider this angle 0, so this point is like, let's say this angle is 90 something, 92 or something, or this angle is I don't know, 270 something. So these two, radius and angle, they are polar coordinates. I will talk about it, what it means. So you need to know golden angle. We know that if now, by looking at that video, you just realize if you generate one seed here, and then you travel 137.5 degree, and then you add another seed, and then you travel 137.5 degree, add another seed. This is the optimal positioning, and then you just like keep going and generate seeds. You just get further away from the center, and you create seeds more and more. So that's the golden angle we know. So then we have step size variable. So you might just come and say that what if you want, just give me the option to generate points around here using other numbers than golden angle. So step size is actually like we're gonna generate a variable that we see not just the golden angle but all other angles as well. So let's start programming. So as I told you, we need number of points, we need position of them, radius, angle, golden angle. So we need these ones. So I start with creating defining a bunch of variables. So what are these variables? Variables are kind of like x and y in your mathematical formula and word. Okay, so we have different type of variables. You know what is integer, which means they are full numbers. Vectors, it's a combination of 3 numbers, and floats are numbers that can accept decimals. So let's start creating them in Houdini. So okay, we are in Houdini. Let's start with a geometry. So you can follow me step by step. So I call that a golden ratio. Over there, we start with a very basic attribute wrangle. So just type wrangle, and you just get attribute wrangle over there. So, and then when I press P, I can start writing here. So, but I'd like to press Alt and E to make it large and nice here in the middle. But the point is, once you start writing, you just have to constantly apply, so it just transfers from here to there. Okay. So first thing, we want to know how many points you want to spawn and generate around. So let's say a sunflower seed has, like, let's say 200 points. So let's call integer count. So let's say you may want 300 points. Sometimes you want 400 points. Then you just say, okay, what if you just leave it to me? Just make a channel or a slider integer, channel integer. Let's call it like number of points, or I don't know, count. Okay. And close your parenthesis, and then semicolon at the end. So if I apply, you can see if when I click on that slider, oh, it gives me count. Okay. So at the moment it just goes up to 10, but if I click here on my this cog here on top and say edit parameter interface. Oh, you see, oh, the count is there. You can click it and say, okay, I just want this to go up to like 1,000, which makes more sense. So let's say then you have 1 to like 1,000 points slider, which is pretty convenient. So, okay, so we know how many points we want. And then you might say, okay, so where these points needs to be positioned. So position is like, so these points, so from this, if you call this center, this is center. And these points are positioned differently everywhere, okay? So this position means like this point has an x and y position, and if it would be in the space, as x and y and z position. So this, so to say that this point, where this point is located, I need 3 numbers, which means that it's a vector attribute. So I type vector, and so I create an attribute called position. I keep it empty at the moment. So it's good that like you just start to add like these descriptions, backslash, backslash. When you do, you know that this is not a command. This is just a description. So this first one is number of generated points. This first one. This second one is, so I do that. Even you do this, you know, tagging and, you know, descriptions just for yourself. Not, well, it's amazing for the next person who wants to work with your codes, but it's amazing. It's very useful for yourselves too. So this one is position of the points. Okay. So what else we need? So sometimes, so let's say I position all these points here, but sometimes you might say, okay, I just want to move this flower here, move the whole system around. So this is the transformation of the whole system. It's like I just want that. So you remember that in Houdini you have this transform node. I want to create this transform node within the body of my code. So forming the whole pattern or whatever. So then I create a vector. I call it T at the moment. And so basically what I want to do, if you create a transform node here, you will see that if you just like each one of these are Tx, Ty, and Tz. So it's a channel, like a translate channel. Actually, if I go to the expressions, or so let's say if you want to say that my rotation would be equal to my translation, you just type Tx. So then the rotation, this rotation would look like that. So what I want to say is just this T is just basic translation. It's a channel. You can bring it out as a slider. Just type channel V, which means a vector, and put it in a and name it, translate maybe, or transform, and finish it. So if I apply that, you see that I get 2 sliders this time. Click on that sliders. Well, I get 1 slider and 1 X, Y, Z kind of vector setup attributes. Okay, so now I know how to. I have defined where these so the position of these points, but like I have to realize how far these points go from the center. So let's say this point. So when our system starts to generate points, it creates the first point, then the second, then the third. Then for the next round, you just say, hey, don't put it on top of each other. Just step back a little bit and generate there. And then step back, generate there. So you see that from the center, the radius is getting further and further back. So we need a radius. So I call that maybe how far points are positioned. And so you will see that it's just one number, this radius. It might be like, let's say this one might be 2.5. This one might be 5.7. So what kind of attribute I should generate, Tim, now? A float, because integer, if it was integer, you could not get 0.7. So integer means just 5, just 2. But like this radius is not 3 points, 3 sections. It just has one section, and that section can accept, decimals. I keep it empty for the moment. You can say that the radius is 1. But when you don't do anything, you just say, I generate this variable, but I keep it empty for the moment. Okay. So when you create points, you spawn a point here, then you move an angle, then you generate another point. Then you move that angle, then generate another point. This angle, let's call it theta. So you know, in math it's just like a Greek naming of angles. So this is an unknown angle, and if this angle would be equal to 137.5, then it is a golden angle. Otherwise, it could be any angle. Okay. So now let's create a float theta, or so just the unknown angle for for rotating and positioning the next point. So it's a theta, and you can say that, okay, the theta is equal to 137.5. This is now a golden angle. But you might say, okay, you know what? I just want you to define it by yourself, by a slider here. So just channel F this time, because this is a float. When I type channel, I mean that I'm going to generate a slider. So channel F, and so again, I should reinforce that whatever yellow that comes after backslash, you can just ignore them. When I type it, you can type whatever you want, or just like don't type it. Okay. So but whatever out of those are the codes that get executed and are important. So now, I just wanted to create a slider, right? So I just type the theta could be the rotation angle or whatever. So let's close it. So when I apply that, and then click on the slider, I get the rotation angle. So I can tell that the angle is 1, 2, 3, 4, whatever, or it's 360 or 90-degree angle rotation. So now what I want is, so you remember that I set radius here. So at the moment the radius is like, at the moment, I just keep regenerating it just for make it clear. At the moment, this is the center. You say that, okay, generate point 1 at this distance, rotate theta degree, generate it again, okay? And then rotate again theta degree and generate another point. But once you get there, you just like, once you are finished, then you have to say that, okay, you've done this round, now move on, extend this radius, get extended, and then generate point. Then once the round, you just positioned a lot of points, then move on, move forward, and then, so this is kind of a global scaling of the radius. So here you saw me, I just said radius scale. So this is like what we can control it. So I add it within this, the scaling of the radius, or the global scaling, overall or global scaling of the radius. It could be another float, but like you can see that when I say this is just a name, radius scale. That's a misspelling, sorry. Radius scale. So this is just a name, and when I say that it's channel F, and I just, you know, put a name for it, a green, when it's scale, and then, so when I create a variable like this, I literally say that this is nothing but what you just appoint here. So some might say, so what this variable does at the moment is just this variable waits for you to tell that, so let's bring it to tell what is the radius scale. So it doesn't do anything because we have not finished our coding yet. So what else you might need? So you might say that, okay, what about golden angle? So like you define the theta, like, which is an unknown angle. So maybe you just need to tell us that there's a golden angle as well. So like, so then let's define it. So let's say float golden angle, which is equal to, you can say that is equal to 13.7.5, okay? But you might say that, okay, you know what? I'd like it to start with golden angle. So let's say when I start, but then I want to say that, okay, what if I go beyond golden angle? I just want to add to it, or what if I want to subtract from it or add to it? Then it's here you just say that, okay, let's add to it whatever I want here, a slider. Let's call that slider, I don't know. So let's create a channel float, which means a slider like this, a float slider. And I like call it angle offset. Make sure that when you write, so don't use space bar. So let me show you what happens if I use spacebar instead of lowercase or underscore. So I generate it, and when I click on that, oh, you probably see, oh, nothing happens. It's because that name is not valid. Now you see that, oh, it's there. So this is just an offset from golden angle. Okay. But before moving forward, I am going to tell you another way of, sometimes you might just say, okay, this is a circle, and everybody says that there are 360 degrees around this circle. But why? Why it's like that? There's a good video on how the number systems created. Okay. Now we just use it like, because we have heard it every day, we just use it. But there's a more intuitive way of thinking about like a circle. A circle like has a radius, right? You might just say that, okay, so let's start. So have you guys drawn a giant circle on the beach? When you want to draw that circle on the beach, you just you just stick something like on the sand, and then you just grab a string and tie it to there, and just on the other side with your finger or with another I don't know, stick, you just like start to walk, and then like you just create, well, a much better circle than this. Like you just create a circle on the sand. So like this. Woo. I'm terrible at drawing a circle. Anyway, you just create a circle, right? You might just grab the same piece of rope or string that you used and say, okay, how big is this circle? So you just put it and measure it. 1, 2, 3, 4, and so you will realize that your circle is about 6 and something. Now we know that it's about 2 pi radius. So 2 pi number radius. Pi is 3.14, right? So it's about 6.2 something. So this 2 pi is called 1 radian, which is basically based on that radius. So so this is like a better way of saying that how big is this circle. You just define it based on the radius, not based on the degree. You just say that, okay, I have a circle that has a radius, and this circle is 2 pi radius, and that is called radian. So actually I have a video for you here about that. It's just 3 minutes.
Now, so far we've been measuring angles with just degrees, but it is now time for us to start measuring angles with a different measure altogether. We call this measure radians. So let us dive right into this topic and explore this introduction to radians. When we think of a full circle, we know right off the bat that it is made up of 360 degrees. Now, if you think about it, this 360 degrees representing the angle of a full circle isn't the most intuitive thing on Earth. To a large extent, we memorized it so deeply that we're fine with just using it. But there is perhaps a better way to measure things like the circumference of a circle or an angle of any sort, and it is through the use of radians, which sounds a lot like radius, and this is not a coincidence because they're actually quite closely related. Now, let's take a look at a circle to help us define what a radian is. 1 radian is defined as the amount of angle that would make its arc equal to the length of the radius. Now, the arc can just be described as any smooth curve joining 2 points. So again, here's the radius, and 1 radian is just however much angle is needed to make its arc equal in length to the radius. Good. So now we must ask ourselves, how many radians would make up a circle? A similar question in degrees would give the answer of 360 degrees. But hang in there a second because radians will make a lot more sense quite soon. Let me start by asking you a question. What is the circumference of a circle? Well, it would be 2 pi r, wouldn't it? Great, and what does that r stand for again? It stands for the radius of the circle. Alright, now how many of these radians would we need to wrap around an entire circle? Well, that would depend entirely on how long a single radian is in terms of its arc length. And since the radian itself is defined as the angle that makes up an arc length exactly the same as the radius, all we would have to do is divide 2 pi r by r to get the number of radians that make up the full circle. Therefore, the answer is just 2 pi. Easy. So 2 pi radians, which is roughly 6.28 if you actually simplify 2 pi, make up the angles to a full circle. So what we are saying essentially is this then. Since 2 pi radians is 1 full rotation, and since 1 full rotation is 360 degrees, then 2 pi radians is equal to 360 degrees. Now, following the same logic, if we divide both sides by 2, we'd get pi radians is equal to 180 degrees. Furthermore, if we divide both sides by pi, we'd find out that the value of 1 radian is equal to 180 over pi degrees. Pretty cool, right? So there will be quite a lot of lessons on trigonometry and the unit circle that...
Okay. So you will see me, because of that, it's way better if I, instead of just a degree, I just say that I want the radian. Actually, here you see that me like say I want the radians of this golden angle, and it's easy to define it in, because when it goes blue it means that it's a command. So I'm just saying that, okay, so I know the degree, you just give me the radians of it within, so like it's a better definition of the amount of rotation. So one last thing before we move on, you might just say, okay, you know what, I want to have a more control over this amount of sections that I create. Okay, so you might say that this pattern is going to be used to generate a optimal golden ratio based stuff, but I want to have, like, what if it goes differently, then give me a chance to create a step size. So then it's comes like, this is step size for generating different kind of slices or different types or whatever, So I generate a, well, as you might guess, another variable called step size. And this step size is actually, I want to be able to, so as I said, you might say that I have a full circle. it's 360 degree, right? And then say that, okay, out of this circle, I just want it to be like, I want half of it, or third of it, or fourth of it, like, or 137th of it, you know? So it's basically 360 on a number, an x. And you know that, like, we just get the radians of 360, okay? So you just go and type in Houdini radians of a full circle divided by something that I would say. So you can say channel F, and I create a step size there, right? So I can apply, and then when I click that, step size is there. All of them are 0 and do nothing. Okay. So now it's time to. So we have defined our variables, and we know what they do. So before I move forward, you want all these variables to be generated just once and not constantly. So here, make sure that your run over is detailed only once. Okay. So then it's time to move on, and one more. There we are. Okay. So now we're gonna start. So so far we've been just talking, you know, what we need. Okay, we need a number of points. We need to know where they are, and then you just say, okay, stop talking and just give us a code that does the job. So then, so far, like we've been like, we had this empty space. Then you just said, okay, there's a center, there's a point, there's another point, there's an angle, there's a radius. So we've been just defining our work, but now it's all about the mechanics. Now we wanted to generate the machine, something that does the job. So I'm going to talk about these 4 loops. So these 4 loops, this is just a loop, okay? These are iterations. So let's say you want to wash the dishes. So what is the for loop? You just say that, how many dishes do you have? Dishes. You get, okay, I've got 10 dishes. You just say, okay, wash dish number 1. Once finished, go wash dish number 2. Finished, go 3, and I up to number 10. So then all the dishes are done, right? So you can say that instead of like 1, 2, just keep saying that, you can say for dish number I, wash it until you come to I under 10 or equal to. So this is the mathematical way of saying it. So you have one iteration, you just execute a command until you come to 10. Because you don't want, you come to 10, you don't want to wash the dish number 11, 12. You know, if you let the machine or the goes, like it goes crazy, okay? So for now, the loop is like this. Position point number 1, rotate that much, like theta, position that point, keep rotating, theta angle, another point, keep rotating, another point. And then once you come to the full circle, move back, so expand the radius, and then again start to put points. And then move back, put points. and then move back, put points. So like how we can define such a thing in a for loop command. So let's start. So I can say that it's a for loop kind of for iterating the actions. Okay, so it's, well, as it says for any, so let's create an integer called I, which is 0 at the beginning. There's no point. You just say that, okay, so first check if we have, so I might say create 20 points. Just say, okay, check if we are beyond 20 or below 20. If the I is below, or the number of iteration is below the number of points, then go to the next I. So then it executes whatever is I'm gonna tell you later on. Once you have executed it, go to the next I. So you can say that, okay, I plus 1. So in other words, I is 0. So if it 0 is below, let's say our count is 20. Okay. So 0 is lower than 20. So then it executes whatever I'm gonna tell you. Then go to the next I. So it goes to I number 1. It's below 20. Yes, execute. I number 2. So instead of 1, I can say I plus plus. So if you see such a thing, it basically means I plus 1. Okay. So this is the loop that I generate. Then you have to add a I forgot the name of this sign. Curved parenthesis or bend parenthesis, I don't know. So this means that the machine begins here. So here I press a tab just to, say that whatever happens here belongs to this, just for sake of keeping things clean. So here you would say that theta angle is you remember that I was saying that the angle at the beginning is the golden angle, right? So you can say that. So here you see me I defined the golden angle. Then I have also defined the theta, where it is. Yeah. So I say that theta is the rotation, and also I have the golden angle. So I can tell that, okay, so theta is equal to golden angle, right? So that's our first definition of, but I do something else. I say that theta is equal to step size. Because you remember that I said, okay, what if I want it to be different than golden angle? I just want to manipulate it. Okay. And also I can say that it's equal to is plus equal to step size. In other words, if you just want to say it's a step size plus 1, instead of that, sorry, yes, instead of that, you can say that plus equal. So now we have defined our angle. I just want to define to radius as now. So radius. So again, for any iteration, it goes and does all of that. Radius is equal to radius scale. So again, like this radius, how much is it? It's the scale that I would tell you. So here you see that I have radius scale. How far this radius goes? That much. But you can do another thing. You can say that, okay, you know what? I want, because if it would be a constant radius, if this radius would be just a radius scale all the time, it just goes and back and just overrides itself. But you want to say it's a radius scale, but it just then, after the first round, it just goes a little bit further, and then more, and then more. It just expands. So for that, you need to say that, okay, so how many, so like the radius for the first round is like, let's say r, first round, okay? First count, every round is 1I, right? So the next I, it would get smaller, get closer, or bigger, you know, or bigger. So for that, you would say that, okay, radius is equal to radius scale multiplied by, so let's say I, the number of iterations, and like divided by count, because you don't want it to be like, so let's say if you have 20 points, okay, the first point would be like 1 to 20, like, so then it just gets like that much expanded, 1/20th expanded, then it gets 2/20th expanded, and at the end will be 20 by 20, which is equal. But as you have realized, this way is like, if I say that, if I tell that like radius scale multiply by I divided by count, it looks like this. But it's better to say that, actually, yeah, it's nice to say that like it's multiplied by I. So then, so let me just say that we have a radius. If you multiply it by 1/20th, so we have 20 points, count is 20, and then the first iteration, the first I is 1, right? So 1 divided by 20 is this. So radius will be multiplied by 1/20th. So the first round of points would be positioned here. Then you go 2 by 20. So the second round would come here. Then 3 by 20. So as the iteration goes up, the third round comes here. And then when you reach to 20 by 20, you reach to your full radius, which is basically 1. You reach to your full radius. Okay, so that line means what I just said. So, but there's one issue here, and that is called casting. I'm going to do a casting here. I talked about casting last week, which means that, okay, so these iterations are integer, right? But radius, so iterations can be like 1 round, 20 round. You cannot say that 2.5 iterations. It doesn't make sense. But you can say that the radius is 3.7. It's float. But iterations are integer. So here you just say you have to convert this integer to float, because now we're going to do it, use it for a radius. So here you just do like float I divided by the number of counts. So that will be so then, so we know the angle, we know the radius. Now it's all about positioning. So like, let me just go here. We know the angle that I'm going to go. We know the radius. But, so let's call this theta and this called radius. Radius and theta, or radius and angle, they are polar coordinates. Theoretically, they should be enough for us to generate points, right? But Houdini works with another coordinates, which is Cartesian coordinates. So we have to be able to convert radius and angle to what is Cartesian coordinates. Houdini says, I don't care what is the radius or what is the angle. Just tell me the x and y of the point. I want that. So I want the x and y of this point and the next point. So just tell me x, y, and I position the point where you want. If you want it here, just tell me x and y, and I position it for you here. I have no idea what is this radius and this angle. So this is called polar to so we are going to do a polar to Cartesian conversion. There's a very good video here for you on that. I'm gonna play it now. Let me go back to, so
Hi, I'm Deborah Fowler, and I'm going to talk about polar to Cartesian coordinates. Suppose that you have a point. You can divide that point by the distance from a point and the angle from some reference axis. These are polar coordinates. But the problem is we're used to working in Cartesian coordinates. So how do you get your polar coordinates into Cartesian values, x and y? Well, we can drop down the perpendicular, and then we have a right-angled triangle. So we can work with trigonometric properties. So for example, the x value is the adjacent over the hypotenuse, which in this case, the hypotenuse is r. So we can take that definition and...
So you remember from last week that we talked about sinus and cosinus. These are like trigonometry concepts, which is pretty easy. So like adjacent, edge or divided by your hypotenuse, it gives you the cosine.
Substitute the cosine of that angle equal to x over r. If we multiply each side by r, the r's cancel on the one side and we get an expression for x. X equals r cosine angle. So we can use that as our x component. That gives us our x coordinate. We can do something similar with y if we use sine, because that would just be opposite over hypotenuse. So using the same technique, we now have the y coordinate for our point. So we have r times sine angle. Once we have those coordinates, we can define our properties of our points. And in fact, really, this is defining a circle as well if we keep r constant and move around 360 degrees. But what if we didn't keep the radius and the angle the same? What if we changed instead the angle to 137.508? Well, it might look something like this if we kept the radius the same. But that's not quite what we want. So what we want to do is also vary the radius. So what we're going to do is we're going to grow the radius out a little bit, each time we rotate around 137.5 degrees.
This is what I
And if we
said about
continue
the
in this
expanding.
fashion, what we get is a pattern that's called the phylotactic pattern, first described by Vogel in 1979. For more information, please visit.
So check her website, Deborah Fowler. She is a professor on visual effects, by the way, a professor of visual effects in SCAD in Georgia. And you see that like how important is the basic concepts of math behind more advanced visual effects if you want to get into it. So now we want to do that conversion in Houdini, right? So let's do that polar. So like what you just heard, let's do that polar conversion. Stop. Okay. Oops. So let's do it. So I'm gonna. So you remember we said that each point has a position. It has position X, position Y, and even position Z, because it's not just in one. It's not just in one page. It's in a space. So it's the cosine of. If you remember the video, if you like, I can play it one more time. No, I'm not playing, but just getting to that point. So x is the cosine of the angle, r cosine of the angle, radius multiply cosine of the angle, and y is the radius multiply sine of the angle. So I'm just basically writing that. So actually you can type radius multiply cosine of the angle. Our angle is theta, right? And we have already defined it. So, and then this one is radius multiply sine of the angle. So what I am writing now is basically I'm writing the same thing in a different language, in a different coordinates. I'm just converting coordinates. So the z is not important at the moment because it's not. We're just generating it in one page. However, I'm just writing something. Actually, let me just keep it empty because I want to generate it and then show you what happens. I apply that. It gives me some error. The reason is I have because this I think it's because of that. No. Oh yeah, you're right. Yes, thank you so much. The reason, no, I just wanted to close the bracket but yeah, the reason I just didn't close the bracket because I wanted to show you that it doesn't do anything. Radius scale. I have a misspelling here as well. Terrible English. Okay, right. We're okay now. So when we don't see anything, you know. I should see 20 points and do that. The reason is we just have defined the math. Now you just have to say, okay, now give us the points. Add point. Add point is a command. You can say add point. So like where these points are supposed to be generated. So one side would be 0, one side would be, so these points, one side of them is the center, the other side is where they are. Instead of center, you can type geo self, which means that when you do that, this geo, it's a geometry node, right? If you move this geometry around, it moves with that. So it's the 0 is a local 0, it's not a global 0. So geo self, whatever it is, and position. So when you apply, you just see 20 points here. You might not be able to see it, so that's why I pressed D on keyboard. And then go to the background and make the background dark. So okay. So the reason that I just see one point is because the point, I have 20 points, but they are all positioned there because there's no radius scale. So when I expand the radius, you see that, oh, they are expanding. So let me go to, let's say 1. So let's expand them to 1. So these 20 points are like top, generated one after another, which each iteration without any rotation. But once I start, so you can start adding rotation or scale or rotation or a step size. The step size is the one that we've been trying to, discussing, like 5 steps. So let's make 1,000 instead of 20. So step size are those sections, 5, 10, or if you just go through numbers, you just suddenly see those beautiful patterns. I am going to just finish this with, so you saw me introducing attributes and then like using it and generating points. If you remember, I just said this translate, which is this T is just for moving the whole system. So you move the whole system up and down and 0. Why you don't see any movement? Because the position of these points at the moment is just the radius. You see? But you have to say that, okay, this is the time that I'm going to use this. I told you that I have a vector that is translate. Use that. So these points should be in where the x is. So t dot x. So translate of x plus that position of x. Translate of y plus the position of the y, which is this Cartesian conversion. And z is basically just z, there's no conversion over there. Let's apply that. So now you can see that this should start working. Yeah, x, y, and z. And rotation is basically just this rotating, one rotation. So, and you can go and just have more rotation. Or you can even type $t, which is time. Every second it does like, I don't know, 10 rotation. And then real-time play. So I just delete that, Ctrl-Shift and delete, and just 0. So so we are almost done. We created what we wanted, but like just to make it a little bit cooler, you might say that, okay, this is a nice distribution of points from the center, an even distribution of the points. Let me just show you a little bit of math again. So if you say y is equal to x, what is the graph for that? Do you remember? It's just straight line, right? In the middle. But what if you say y is equal to x to the power of 2? The graph is like exponentially expanding, because 1 1, it's 2 4 3 9, so it just like exponentially expands. So if you want these points to just suddenly like the change would be exponential, like, so if the position of the points would be like this is linear, but if it would be like this is exponential, exponentially lowering, or exponentially expanding. So you saw me like say that x to the power of something, we have a power function in Houdini, which is POW, power. So you just say that the power of, so if I wanted to write down that, I would say power of power x n. That's how I write it in Houdini. So where to make it exponentially? It's here. It's basically radius. So the radius of the points could be the power of and then float I. So this is a number, right? And then the next one would be something that I say. A channel float would be, let's call it fall off. Actually, I should put the fall off in a quotation mark, close that one and close it again for the whole thing. So you see that when I close that one, it says, oh, you just closed this one, but that one not closed yet. When I press another parenthesis, it says, oh, you just closed all of them. So here I am saying that the radius from the center to that point are getting exponentially changed by the number I say. I apply that. Oh, suddenly you just see this weird thing. I get the fall off slider and I play with that. Look at that. It's gorgeous. So you just generated something very interesting with a bunch of codes. I call that golden ratio VEX. Let me save it. And it just works so fast without any problem. I'm going to lower down these number of points. And what if I connect these points together? So you can connect points together with a very simple, you see me, I generated the source code, which is this one. Apply and accept. So I don't need to do any more coding. Now I'm ready to do some stuff on it. So I have everything I want. So I can just start and add a node called that add. And this node, actually you can polygon by group here instead of by pattern. Create polygon by group. So it says that, okay, so you have a group of points, which are these points, these blue ones. Let's group them and make a polygonal shape out of it. So then this becomes very interesting. So when you start to play around with these this step size, you suddenly get like incrementally like exquisite, beautiful shapes. And if you play with this fall off, it just like changes into like something very interesting. And this step size is very sensitive. But if you remember, like if you just put whole numbers, it gives you like shapes like this, or 3 like 3. But if you just go to the decimals, like suddenly it just gives you amazing shapes. That you can use it like, as I have explained here in this slide, you can start using it for generating a kind of a flower pattern for a flower or for a botanic generation. So I'm gonna just finish it with a just simple shape generating. So you saw me. I could rotate it. At the moment it's just facing to the z direction. I can rotate it to the to flatten it on the floor. If you get the spikes that are just like the very first one is just like a little bit crazy, like what you see here. Sometimes in the middle you get like, you know, these lines. You can say that the first, it starts not from 0 but maybe from 2. You saw that that's gone. Before it was 0, because 0 is just like a very weird positioning of something, a point that is in the 0. You can say that, okay, start with 2 points, number 2, and then move up. So just a bit of adjustment on the code. And then, okay, so I would add a add point as I did. You may want to add, so like these points, like you see that they are overlapping sometimes. So to avoid any problem with the overlaps, we add a fuse node here. I would like to show you what this fuse does. I keep it back to this number, but you see the fuse node kind of like merges points together and just tries to like combine them until they become like one. And the area that it merges is defined by this distance. Okay, so like we've got a bunch of points, but let's resample it to get more points. Resample. Also, resample gives us the direction of this curve. So let me just make a simpler, or like, yeah. So let's say this curve travels through, right? So what if someone says, okay, tell me an attribute or information that talks about how this curve is traveling through this line, I would say, okay, after resampling it, actually I might need more the length to have a better resampling. So you see that the points are becoming more points or less points, you see? So you might say that, okay, so it's not just about like more points, this resample node. It's about this curve u attribute. I want to generate curve u attribute. So see, before that, when I middle click, I don't have curve u, but after that I have this curve u attribute, which is basically how this curve is traveling forward. Now I have to be able to send this curve u attribute to the points, because I want these points to understand the direction of the curve. So I can use an attribute transfer. I just typed attribute t, and I say, okay, grab curve u to the points, curve u. Yeah. grab curve view from them and apply to the points. So now these points have that attribute applied. Actually, I would be able nice if I drag it from here. Oops. If I, yeah, so it would be on the floor. So now these points, so like if I click on this normal, they don't have any normal, because it means that they don't have any directionality inherited within them. So then I add another attribute triangle. This is a very commonly used command. It's a very easy command. You just say, okay, normal, like $sign normal is $P. Their normal is their position. So once you do that, when you click on the normal, you just see, oh, suddenly you get this like nice thing. Do you remember that their position was tiny? So if this pose X, pose Y, pose Z, it was tiny when they were close to the center, but when they were getting further back from the center, it was getting larger and larger. So the position gets larger and larger. So now I want it to raise in this direction as well. So like in this like spiral way. So here you see me, I'm using the channel ramp for that, and I use the direction of the curve as well. So let's do it. I add another. So actually this one was to generate normals, and this one is for raise points in Y direction. Okay. Here I just simply say, okay, now these points, so each point has a position, right? So $sign position, but in Y direction is basically, I'm going to give you a ramp, a channel ramp, which means that I want a ramp here, that this ramp has two values. The first value is Y offset, or when I put it in a quotation mark, it means that it's something that I define. It's nothing that exists in the scene. But the second one is $sign curve U, which we generated earlier here, right? Which is the direction of this curve. So it says, look at the direction of the curve, and then based on a ramp, raise it. Okay, so is there anything happen? No, because you have to generate the ramp. Suddenly get this. The ramp looks at like those curve and just like raises up based on this offset. But like you can play with that. You can just like play. That looks like it. This looks like a nice flower already. But one last thing before we okay, so you see here I am kind of color coding these three main nodes. It's because you know, it just like shows me the order of what's going to happen. So let me show you how to color code your nodes. It's just like select your node, press C on keyboard, and color code it. That's it. So I sometimes when I want to color code something that happens consecutively one after another, I just say RGB. So R, the first one, then the second one, then the third one, another attribute wrangle I'm going to add. I go blue for that. So this one, so let me just like do nothing on this one and show you what happens for that last comment. What's the point of it? So let's say you make a flower petal you generate one. So let me just generate in Maya or here, or create a grid. So I'm going to turn off this normal. Actually, I'm going to template that so I see these points. So I'm going to turn that off too, and I just say that it's just 3 by 3, and it would be very small, or maybe 4 by 4. And oops. Okay. So if I say that this is my flower petal, you can use like, I don't know, soft transform. Let's say you grab any one of these points and just say that, okay, I just want to like move them, but in a soft transform, and just like, you know, achieve something based on the radius, and then one on the other side, and do this and do that. I just you know, just like do a bit of modeling. I just use a simple shape, or just let's leave it as it is. So now you can say that, okay, everybody knows about copy to points. So like I've got a bunch of points, I've got an object, copy this object to those points. I get this shape, maybe more points, 200. So I get this shape, but it's like flowers are the ones that are closer to the center, they are tiny, right? So then I go and say, okay, so this code that I'm writing here is for making that one that is closer to the center tinier. So I'm going to make a float gradient, which is a gradient from the center. So there's one very famous code that we always use it, and it's ptnum divided by num pt minus 1. So what that one says, so let's say so maybe you've got like 5 points. If you have 5 points, each one of these points have a number, right? ptnum is that number. Let's grab point number 3. For point number 3, ptnum is 3. But num pt is number of the points. How many points I do have? It's that one. It's 5. So if you want to like kind of find a scale, let's say if number 1 supposed to be small, number 2 bigger, number 3 larger, number 4 larger and larger. It's just like if based on the number of the points. You want to get a nice ratio that works for you. Then just use that ratio. It's here. It's already here. It's already here. Just say pt num divided by num pt minus 1. So it means that like this will be 3 by 4. Then that. So this is 1 by 4. This is 2 by 4. You see that it's getting bigger and bigger. 3 by 4. 4 by 4. And this is 5 by 4. So it's getting bigger and bigger. So this basic things that everybody uses is that. So now let's create another float. I call it scale ramp. A ramp that shows me like, okay, so how I'm gonna scale it. You can use a ramp which is like an easy. So create a channel ramp, and inside that channel ramp you have a slider. Would be nice if you have a slider that's called scale ramp. You saw me sometimes using the double quotation or one. It's just the same, doesn't matter. And gradients. So gradients, we already have defined it, which is that one. And then let's now say that, okay, so I have created my ramp. You see it's there, but it doesn't do anything at the moment because I have to. You know what? Each point that you have in the space, they have a scale attribute inside them. So I'm going to extract and use that scale attribute. I call it fp scale. Its p scale is the point scale, the scale of each point. Each point has a scale attribute inside it. I know a point scale is 0, but like it's an attribute that exists there and you can use it. So you can say that do a fit 0, 1, which means fit it between 0 and 1. This is what you asked last week, Daniela. So like how to fit something within like a kind of, let's say here, between 0 and 1. So here is scale ramp. So I'm going to fit it between this scale ramp, which is this ramp, and a minimum and a maximum. Okay. So I'm going to fit this scale ramp, this one. I don't want this to be like 100 and that one would be 1,000. I want this scale ramp between a minimum and a maximum. But that minimum and a maximum is, you see that it just like goes weird. You might just ask, oh, wait, we didn't define them. So give us a way of using it here by ourselves. So you say that, okay, I'll give you a chance of defining yourself. So channel float min for the minimum and channel float hang on. So here I should use double quotation for the mean and channel float. So this is where like double quotation has priority. It's better always to use double quotation. Sometimes I just use single quotation. Channel maximum, and let's close that. So let's, oh, what I've done. I need 2 of this. There we are. So now you get, so at the moment there's, you don't see anything because minimum and maximum are 0. But I should start seeing stuff happening. 0.01. Oh, yeah. So the problem over there was that like this one, I just turned it into a number. So like this 1.0, you need that to be able to just like. So this radiant is very useful because you can say that, okay, the one that are further away, they are large, and the minimum, the one that are close, they are tiny. These are large. Actually, I can go and say that I want 2000. Ooh. Then you get a nice, oh, 2000 was too much. Like. So just imagine that they would be flower petals. Then you had a nice, so now even now, if you just play with the step size, you get like fantastic shapes. Okay, so that was it for today. Lots of generative art, which is amazing and beautiful.